Katie Carr from the Advanced Digital Sciences Center, and today we're talking with Deming Chen from the University of Illinois at Urbana-Champaign, and he is an expert in hardware accelerators. So hi Deming, can you tell us a little bit about what hardware accelerators are?
Sure. Hardware accelerators are integrated circuits that use customization and parallelization to speed up computational tasks. Currently, there are mainly two types of hardware accelerators, FPGAs and GPUs. Okay. Both of them were invented about 25 years ago, and along the years, the functional capacity and computing power have dramatically improved for these accelerators. Okay. So for FPGA, it means field programmable gate array. Its uniqueness is people can actually program a new design onto the FPGA even after the FPGA is manufactured. Oh. And for GPUs, it contains relatively simple computing cores, but with many of them, usually hundreds. Okay. So they can support hundreds of thousands of threads running concurrently. Okay, so can you tell us how an FPGA and a GPU is different from an ordinary processor? Sure. So an ordinary processor usually has one or several cores, computing cores. But for FPGAs GPUs, they mainly speed up the computations through parallelization. So for GPUs, as I mentioned, it can contain hundreds of cores and to run a lot of threads on top of it. And for FPGAs, you can actually do, besides parallelization, you can also do customization. For example, a GPU is running 32-bit, but for FPGA, I don't need to. If an application, after analysis, I find out 14-bit is good enough, then I just do 14-bit. So I can reduce power, I can improve speed up, and everything. Okay. So in your expert opinion, which is better, an FPGA or a GPU? So it really depends on the applications we are targeting. So for applications that requires a lot of customization, and also if it's integer and fixed point application, FPGA is better. But for floating point applications, and if there is massive amount of parallelism in the application, then GPU will be better. That's okay. So what kinds of applications need hardware accelerators? There are many of them, and examples include, for example, bioinformatics, or simulation, or video and audio processing. So recently, we did a work. It's a collaboration with Professor Doug Jones, who is also associated with ADSC. And what we did is we used GPU to speed up 3D audio applications, and we achieved 500x speed up. Because of that, we can make the 3D audio processing real time. Okay. So why are we not using FPGAs in everything? Like, why couldn't I have an FPGA in my laptop computer to make my Windows XP run faster? Yeah, that's an excellent question. Actually, I also asked myself the same question. So I think mainly because of two reasons. So the first reason comes down to this programmability for FPGA. Currently, people still use hardware language to program the FPGA. And so they are not like software. So this language are pretty low level and error prone, and it takes a long time to program FPGA. For example, we did a face detection algorithm using FPGA. We did achieve about 100x speed up, but it required a hardware engineer 6 months to do such a design, right? Which is kind of unacceptable if we are talking about tons of applications to be run on Windows XP, right? So that's one reason. So the second reason is a cost reason. Right now, FPGA is targeting small to medium volume markets. So if it's a large volume, and then usually a CPU or ASIC is more cost effective. Okay. Yeah. So what is your research group doing to change that? Okay. So right now we are within ADSC. We are focusing on two research thrusts.
Okay.
So the first one is called high-level synthesis. So the problem is instead of using the hardware language to program the FPGA, you know, that's the problem. We will use a high-level language, like the same language used for program CPU, right? The same language will use that to program FPGA. But it's not automatic, so that's why we need a synthesis tool, right? Okay. So this tool will take the C language and then go through a series of optimization steps, such as scheduling, allocation, binding. So in such a way, we can generate the hardware description for the design automatically. Okay. And then we can just take that design and then program the FPGA. Okay. Yeah, so that's the first effort. And the second thrust is to improve the programmability for heterogeneous platforms. So such platforms include both GPUs and FPGAs for acceleration purposes. Okay. And the reason is intuitive, right? We mentioned GPU, FPGA, they are good for accelerating different applications. Yes. So we can have a platform that includes both. But to program it is very tricky, right? A naive way is I'll use GPU language to program GPU and a hardware language to program FPGA, which is very inefficient. So what we did is we use a common front-end language. We just use the GPU language, and then we can go through a transformation that transforms the GPU language into a language FPGA can understand. Okay. So that means we can just use a single language to program the entire heterogeneous platforms. And recently we've published a paper along this direction, and it won the Best Paper Award from a top conference. So this means the community recognize the importance of the topic and really see we had a good breakthrough through this kind of effort. Yeah.
Well, this is great. Thank you so much for coming here today and sharing this with us, and we appreciate all your research.
Thank you very much for the opportunity.
Let's travel to the ADSC offices in Singapore to learn more about this project.
I'm a professor from the Department of Computer Science at the University of Illinois and the director of the Advanced Digital Sciences Center in Singapore. And that's where we are today, talking to Kyle Rucknow and Eric Lane. So we heard from Deming about the overall goals of his FCUDA project. Can you tell me what the state of the art is in high-level synthesis today? Well, what is high-level synthesis? And then tell me what the state of the art is.
So high-level synthesis is the process of mapping a high-level language description in any number of popular programming languages to hardware implementation, in our case, particularly to an FPGA. So mapping something that's fast and easy to produce to hardware that's faster and more efficient.
Okay.
The current state of the art, it involves being able to take unmodified code in C or C++ to add annotations to describe how that code should be transformed to map well to hardware, and then mapping that to efficient implementations on hardware. But our approach is a little bit different than that.
Okay. So how's your approach different?
Our approach really targets those annotations as being a main problem for uptake of people actually using high-level synthesis tools. In our opinion, all prior high-level synthesis tools make a critical mistake of trying to target experienced hardware designers to use their tools, rather than people that produce good software but need that software to execute faster. And we feel that being able to remove those annotations makes it much easier for somebody that can write a good program in C, C++, or a GPU programming language to be able to get the faster, higher performance and lower power consumption that they need without having hardware design expertise.
So why is it so much harder to make it end up on an FPGA instead of a GPU?
Because for the FPGA, the programming effort is a lot. So the programmer has to write the code at the register transfer level, which is very time consuming. The typical design period is more than 6 months. But now with our high-level synthesis, the programmer can easily write the code and compile it within just a few days.
Okay, got it. So how far have you guys gotten? What are your contributions so far?
So far we have tried some scientific kernel like matrix multiplication and some kernels from CodeSTK. That for the performance is comparable to the GPU code, but it only consumes 1/10 of our GPU.
Wow. Okay. I think I want to put that into perspective with a drawing. We've got this spectrum here from software all the way over to full custom hardware. And then let's rate them on speed, power, and the extra design time that it takes to come up with them. So maybe you can help me by filling in some of these entries. If software is our baseline with speed of 1, power of 1, extra design time of 0.
Typically, the GPU will have speed up in the range of 10 to 100x. Power, energy, is often about parity. The extra design time is maybe small number of weeks, so 1 to 2 weeks. With the FPGA in our style, as we were saying earlier, we achieve parity performance with the GPU, so we retain this 10 to 100x performance advantage over the CPU, but we get the energy advantage. So instead of 1, we're at about 1/10 of the power of the original, with the same 1 to 2 weeks design time. FPGA manually designed, so this can be again faster than our current. So it might be up to 500x or greater. Really the same amount of power, because the power advantages that we get are from using an FPGA, not from a particular design style that we chose. But then the design time is 6 months to 18 months. In the full custom, you can get yet further advantages. So this might be as much as 1000x or more. But full custom hardware will, it might be 1/10 to 100th of the power, and design time here might be years. So we can get big design time advantages. We do take a slight performance degradation, but that's something that we're working on improving. We maintain the power, and we have it all without requiring the kinds of very specialized expertise that it requires to do these designs. There may be, they're on the order of thousands of people worldwide that have the expertise to produce good FPGA designs, whereas worldwide, there are millions and millions of people that can produce software programs.
Yeah.
So.
Great. Well, thank you very much for talking with me today.
Thank you.